Okay, all right. So, so last time we were talking about how to use, I want to say this diagram, which is really kind of an organized summary of all the ideas that we've talked about in Chapter 6. So how to use the techniques that we've talked about in Chapter 6 to compute line integrals and surface integrals. And so the big picture idea is notice where you are in what diagram. If you've been asked to compute a flux, then you are here in the R3 diagram. This flux is through, if it's flux through a surface in R3. Right? And that means that you have two candidates, possible boundary theorems that might conceivably apply to what you're trying to evaluate. So, and you have to test and see which ones of those actually apply. So, specifically, take your vector field, compute the divergence. See if you do or don't get 0. If you don't get 0, there is no anti-curl. Don't bother trying to find it. Right? Then likewise, you have to ask, well, what about Gauss's divergence theorem? Well, I would need for my surface to have an anti-boundary, or said differently, I would need the boundary curve to not exist, right, or to be 0. If the surface has a boundary curve, well, then it's not a closed surface. There is no anti-boundary region, and you can't use Gauss's divergence theorem. So you consider the situation, decide which of these theorems may or may not apply, decide which one looks like would be the easiest to proceed with, and off you go. Okay. All right. So let's do some more examples. We did a couple of examples last time. So here we have compute a line integral. Our vector field, you'll notice, has 3 components. That means, now let's go back to our diagram. That means that we are computing one of these. We're in the R3 diagram, line integral. Here's our 2 candidate theorems. Forget about divergence. Forget about Gauss's theorem. It's got nothing to do with this question. It's way over here. Okay, so going back to the question, we have a curve given. It's given parameterized. By the way, heads up, this is going to only subliminally, this is going to kind of psychologically push you toward Chapter 5 methods. Right? It's parameterized. I know what to do with that. You're one step away from just plugging into the formula and plug and chug. And it's not always the wrong thing to do, but here I think it's pretty wrong. Right? I mean, look at that parameterization. Look what you'd be plugging it into. This would be a nightmare of an integral. Okay. Okay, so the 2 questions to ask. Again, here we are. The vector field that we're given. Diagram says compute curl. So let's do it. Compute the curl, you get 0. By the way, it's an easy calculation. Notice there's only x's in the first component. There's only y's in the second component, etc. All the partial derivatives that are going to go into computing the curl are all 0. Curl is 0. So the curl being 0, that means that there is an anti-gradient, and you may use the fundamental theorem of line integrals. Now, there's a temptation here to say, okay, cool. I love this theorem. I remember that one. I'm good at this one. I'm going to do that. Slow down. Consider your options. By the way, look at what we'd be facing here. If I had to, if I wanted to go directly to that, I'd start trying to find the anti-gradient. That's going to be hard, right? I'm going to have to take an x anti-partial x squared e to the x. That's a couple of integration by parts, right? Nobody wants to do that. There's one integration by parts here, and this would be an antiderivative that cannot be accomplished in what we call closed form. In other words, without using power series. So this is really hard to do with the fundamental theorem of line integrals in sort of the straight up find the antiderivative, the anti-gradient sort of method. Okay, so let's think about this a little bit more. What's our other option? Our other option is to look at the curve and ask, is there an anti-boundary surface? Is this curve the boundary of some surface? Well, let's see here. Hard to figure what this curve looks like. Right? That's annoying. But if I want to know if there's an anti-boundary, just think about the boundary. Does this curve start and end at the same point? In which case, yeah, it's boundary. Or does it start and end at different points? In which case, no, it couldn't possibly be a boundary. All right, so let's just plug in. Notice that with t equals 0, t equals 1, just some arithmetic there, but if you plug those in, they are the same point. So this curve, ugly though it is, starts and ends at the same point. This is a closed curve. Right? It starts here, and it goes around and does some funny stuff, and it comes right back. And so it's going to, I mean, you know, barring it being tight in a knot, which it's not, this is a boundary of a surface. So, Stokes' theorem is on the table. Legitimate possible, whoops, I hit the wrong, sorry. Stokes' theorem is also on the table of possibility. Two different options. So we're going to pick whichever one looks the easiest. Now, it turns out that despite what I said a minute ago, it turns out that both of these methods actually end up being pretty easy. And after I show you how they both work out, I'm going to talk about a related point. But for the moment, let's just do one at a time. Let's start with, which one did I decide to start with? So we'll start with the fundamental theorem of line integrals. Here's what the fundamental theorem of line integrals would say. It's f of x of 1 minus f of x of 0, right? F of b minus f of a. And we don't know f, and we were bemoaning a little while ago that it's going to be super hard to find f. And the good news is, because x of 0, whoops, wrong one, because x of 0 and x of 1 are the same point, that means that these are two identical values, and I'm subtracting one from the other, and so I get 0, and we're all done. I don't have to know the anti-gradient at all. I just need to know that it exists, which it does. Everybody on board? Okay. All right. So now we have an answer, so we can sort of declare a victory right here. But I want to go ahead and show you how it works out the other way as well. The alternative, we agree that this curve is where did I write this down? The curve is the boundary of some surface, so I can use Stokes' theorem. Now, another complication. No, I don't know what the surface is. I don't know how to parameterize that surface. I don't even know how to visualize that surface. Right? But I don't have to, because the curl being 0, I'm doing a surface integral of 0, and that is easily computed to be 0. So you get a nice, easy answer either way, as it turns out. Okay. So this turns out to not have been a coincidence. It turns out that when you are interested in a line integral, if both theorems apply. Now, I'm not going to make a theorem out of this. You may not cite the following thing I'm about to tell you on an exam, but just between you and me, specifically speaking, for your future reference, if both theorems apply, your answer is 0. And it's not hard to see. I mean, the point is, if this theorem applies, that means curl is 0. And if this theorem applies, that 0 means you're doing a triple integral of 0, and that means that you get 0 every time. Right? And likewise the other way, if this theorem applies, that means that there is an anti-boundary, which means that the boundary curve consists of, well, 0. By that I mean 0, two identical points, point in itself with a negative orientation. Which means you're going to be looking at something minus something, which will always give you 0. So that's a nice little fact. Now, on an exam, pick one of these arguments and give it to me. Right? So you can't say, Bray said in class, both theorems apply, the answer is 0, ergo. Right? That's not a acceptable answer. But at the same time, it's nice to know what the right answer is when you're trying to argue what the right answer is. Right? So, nice fact to remember. Ditto with fluxes. If both theorems apply, your answer is 0, and you have 2 equally convenient arguments that you can make to make that case. I'm going to leave that as an exercise for y'all to fill in on your own. Try to persuade yourself that in the computation of a flux, where you could use Stokes' curl theorem, you could use Gauss's divergence theorem, it has to be that the result is 0. Okay. Let's see how we're doing on time. Oh, gosh. So here's another one. Another computer line integral. Notice our vector field, 3 components. So again, we find ourselves looking at one of these, and therefore 2 candidate theorems, our usual game. Being as we're computing a line integral, we compute curl. The diagram tells us to. And this time we don't get 0 for this vector field. You take that vector field, plug in, get curl, and it's not 0. So forget about the fundamental theorem of line integrals. It's not going to happen. Right. Going back to the diagram, we took the curl. We did not get 0. That means there is no anti-gradient. So forget the fundamental theorem of line integrals. Okay. Get out of that yellow. It's very harsh. Okay. So can we use Stokes' curl theorem? Well, I've got to look at my curve. Now, the curve is the intersection of that plane and that cylinder. And we did one like this a little while ago. So let me just skip to the picture. This is what we're talking about. Intersection of a cylinder and a plane. You see we're going to have a curve. And yes, that curve is the boundary of a surface. Now, you got to have a picture to make this case. Well, it's really helpful to have a picture to even see what the resulting anti-boundary surface is. You certainly have to have a picture to make the case, right? To explain to the greater me that you know that there is such surface. So yes, you can use Stokes' curl theorem. And does anything nice happen? Well, it depends on how you look at nice, I suppose. The normal vector is easy to write down, right? The vector field allows for this computation of curl. We know that when we're doing a flux, we're doing a dot product of curl with the normal vector, right? So in Stokes' theorem, the flux in question is a flux of the curl. So we're going to be looking at curl dot in. And we saw an example a couple of days ago where by just great coincidence, good fortune, that dot product happened to be 0 and we declared victory, right? So that didn't happen here. So here's the thing. I mean, these boundary theorems, they're not magic wands, right? They will not just, instantly turn your very difficult question into something that's trivial. Often they will, but not always. So this is one of those not always situations, and you can compute curl dot in, and it's some non-zero constant involving 3's and stuff. So you have a surface integral. You were asked to compute a line integral, and Stokes' curl theorem says, well, if you would prefer, instead of doing that line integral, you could instead do a surface integral. And now you have to choose. Which would you rather do? Neither one's horrible. The curl dot in being a constant, really all it is a scalar surface integral, and this surface is pretty easy to parameterize. Right? The equation of the plane is easy. X and Y are clearly going around in a circle. That means Z is easy to write down in terms of, whatever the equation of the plane is. Right? So you've got a parameterization of the Sorry, I got ahead of myself. What I have just done is parameterize the curve here. Sorry about that. That's parameterization of the curve. So, so let me rewind. If you want to do it by a direct computation as given, forget about Stokes' theorem. If you want to use just plug and chug, parameterize the curve and go, it's not that bad. Sines and cosines, the vector field you're plugging into, not that bad. You're going to have a couple of trig integrals, perfectly doable. The alternative, and what I meant to say a minute ago, is the surface. Easy to parameterize because if you know z as some function of x and y, you can use the graph parameterization. Right, and the graph parameterization then turns out to be pretty straightforward. Once you have a parameterization, partials, cross product, magnitude, compute the surface integral. It ends up being pretty straightforward. Given the two choices here, I think I would rather do the surface integral if it was me. But it's, I don't know, could go either way. I would encourage you on this one to work them both out and see which one you like better. Right? They're both perfectly doable. Okay. All right, moving along. There's a couple of examples here I'm going to skip in the interest of time, not because these aren't good examples. I encourage you to look at these examples, but we just don't have time to talk about them. So I want to move on now to this question. Here we are computing a flux in R3. So let's go over to our diagram. We are now looking at one of these. So here's our two candidate theorems. The diagram says compute the divergence and see what we get out of that. Okay. All right. Where did I write this down? I wrote it down somewhere. Well, anyway, it's easy to do. Let's compute this divergence. Here's our vector field. Easy computation of divergence. I get z, that's the x partial. The y partial of that gives me minus z, and the z partial of that gives me 0. So the divergence is 0. Here's a different way to think about it. I already know that this is a curl of something. It says so right here. My vector field is a curl of this thing. Well, if it's a curl, the divergence of it has to be 0 because, again, on our diagram, there is a vector field whose curl gives me the vector field in question. Lifetime theorem says divergence has to be 0. Right? So two easy ways to see the divergence is 0. Okay. All right, how handy. Now let's, what was the question actually? The question said compute the flux. Our surface is the part of the elliptical paraboloid with that equation that's above the xy plane. Now y'all might recall we did one kind of like this in a couple lectures back, Wednesday or Thursday, I forget exactly which one. So there's our surface. And now, very importantly, just the part above the xy plane, right? Not the whole thing going down. Let me caution you about one thing, a constant confusion that comes up for some students. Students are thinking, well, we have this elliptical paraboloid, and in some students' minds, it's easy to conflate the surface, which is a two-dimensional thing, with the solid, that the mass, this three-dimensional region underneath that surface. But very importantly, these are not the same thing. So if I were to say the part of the paraboloid that's above the xy plane, some students, again, it's really easy to make this mistake, are thinking, okay, well, I have this great big solid down here, which we don't. Thinking great big solid, looking at the part above the xy plane, and then you see, okay, well, I have a lump. What I'm talking about is a lump. Oh, wait a minute. No, it's a surface. Okay, so it must be this paraboloid and this little bit of the plane underneath it. I think that's the what's going on in the mind or something. But very importantly, we're only looking at this surface. Look at this equation right here. This does not say z equals, polynomial or 0. Right? That's not what this says at all. It says z is equal to this function and specifically equation of a paraboloid. So it's just the paraboloid. We are not talking about that surface down there as well. Is everybody clear on what's going on here? All right, if you make this mistake, here's what a lot of students will then subsequently do. A lot of students will say, oh, well, we're looking for a flux, and a flux is a triple integral of divergence, which we just got through computing, was 0. So I have triple integral of 0 equals 0. Drop the pen, move on to the next question. This is worth almost 0 points on the grading because this makes no sense at all. And furthermore, this has nothing to do with the actual solution to the question. Right? So this is kind of a landmine situation. You got to be ultra careful, super heads up. Don't do this to yourself. Right? You got to pay careful attention to. Wait a second. What exactly is my surface? Parse the language extremely carefully, right? Think it through. Notice in this case, this is not a closed surface. This is a upside down cereal bowl. There is no lid underneath the cereal bowl. The cereal is all fallen out. It's empty, right? It's an umbrella, right? It's not the boundary of a solid. So this is. That's wrong because there is no solid whose boundary is that surface. Everybody on board? Okay. Let's get rid of all that junk. Okay, so back we are to our situation. We've got this surface. Now we did compute that the divergence was 0. Right, and that's nice. And by the way, this tells me that there's an anti-curl, and furthermore, I can see the anti-curl. There it is. You got to think this one through, right? It's easy to look at this and think that this is the curl because you see del cross makes you think curl, but it's the curl of this thing that is F. Therefore, F being the curl of this. This is the anti-curl of F. Everybody on board? So this is my little sneaky way of giving you for free the anti-curl, right, that we can use in Stokes' curl theorem. So going back to the diagram here, the vector field was given to be the curl of this thing. That's the vector field that I can use in the Stokes' curl theorem. So option 1, I'm going to call it, is you can take your surface, look at the boundary curve, and then do a line integral over that boundary curve of the anti-curl field. And that works out really nicely algebraically, and here's the algebra. There's Stokes' curl theorem. Line integral of the anti-curl, and the integral ends up being 0. I'll let you guys read through the mechanics of that. Okay. All right, another option. Now, of course, you might have seen this one coming, and so when we did see a question like this one previously, we were looking at a surface that looked a lot like this one, and we made a different argument. We used surface independence. So that's another freebie that you get when the divergence is 0, right? The divergence is 0. There's several equivalent conditions, and one of them is pick your favorite surface. So with the understanding that the boundary is this right here, that's the kind of the lip of the cereal bowl, if you will, right? That's the boundary curve. What's my favorite surface that has that as its boundary? Well, it's the flat surface there. Forget about S. I don't like that at all. That's curvy. Yikes. Right? This nice flat one is much easier to work with. Excuse me. Oh my God. Yeah, you're welcome. Instead, it's you don't have to cite anti-curls and Stokes's curl theorem. You can just say surface independence. I'm going to use that surface, and here's what your calculation turns into. So again, we don't like that surface. We much prefer this other surface. Vector field doesn't change. Our new surface has a normal vector. It's easy to write down because our new surface is flat. This dot product is obviously 0. Done. So take your pick. Both of these solutions work out really nicely, as it turns out. Everybody on board? Right. So you can use Stokes's curl theorem. You can use surface independence. Remember, this is how I draw surface independence. I mean, it's, anyway, that's an argument. But you cannot use Gauss's divergence theorem. Don't make that mistake. Again, it's such a landmine tragedy to happen. If you use Gauss's divergence theorem, it's got nothing to do with a valid solution and is completely invalid, makes no sense whatsoever. There is no such thing as that solid. Nothing's right. So it's typically a 0-point situation. Okay, all right, enough warning on that. Okay, let's see, moving along. These last couple of examples go pretty quickly. We're computing a flux. We know where we are in the diagram. Our surface is the unit sphere oriented outward. We've got a vector field given to us. Right, so we are here. We compute the divergence, and the divergence is 1, which is not 0. Oh well. Right away, because that's not 0, I know there is no anti-curl. Forget Stokes's curl theorem. It's got nothing to do with anything. Forget surface independence. Can't use that either. Right. So our only hope, for this is maybe Gauss's divergence theorem. So for which purpose I would need an anti-boundary. Is there some solid whose boundary is our surface? Well, let's see here. Our surface, the unit sphere oriented outward. Yeah, right, the unit sphere oriented outward. The unit sphere oriented outward. That is a boundary. It's the boundary of that ball. Right, so instead of the flux, I can compute a triple integral over the solid of the divergence. I've already computed the divergence. Divergence is 1. I'm looking at a triple integral of 1 over a barnyard variety geometric solid. Easy integral. There you go. Everybody happy? Questions? Pretty good. A lot of details in each one of these examples. I'll just remind you real quick. One of the big points I want you to be digesting as we go through this is how all of the ideas that we're talking about really. This is the board on which we play the game, and the patterns are always the same. Right? So I hope you'll try to organize your understanding of these ideas from the point of view of what's happening on this diagram, how do things fit together as suggested by this diagram. A lot of value in that. Okay. All right. One more example. This is a nasty one, or so it appears. I give you an ugly vector field. It's pretty ugly. And then I say, compute the divergence of that. Okay, already, yikes. Right? Ugh, that's a bunch of partial derivatives and oh my gosh. And then you got to do a triple integral over the ball of that. And oh my gosh, that means our bounds are either going to be have square roots all over the place, or if we do it in spherical coordinates, then we're going to have more trig than we already had. it looks like a nasty problem. The foot in the door here, of course, is to realize I've asked you for a triple integral of divergence, and that screams Gauss's divergence theorem. Here, let me do this in a more gentle color. Triple integral of divergence. It says, well, you're really computing a flux. All right, so let's look at that flux on the surface. Okay. So our vector field, the vector field whose divergence we were doing a triple integral of, we are now doing a flux of it. And then you might think to yourself, well, this still looks pretty nasty because now I've got to parameterize the sphere, and still with the there's some trig in there, and it's could be annoying. Always be on the lookout for your good fortune. Look for symmetries and that kind of thing. In this case, it's a geometric coincidence. I want you to be on the lookout for. It turns out it's really easy to write down the normal vector here. Our normal vector. This is a sphere. Right? Spheres are great. Lots of symmetries, and specifically the normal vector always points directly away from the center. If the center is at the origin, that means that the normal vector is always a scalar multiple of the position vector. In this case, it's 1/5 of the position vector. We've made this argument several times in different contexts. Your antennae should spring up every time you see sphere and think, hey, I know what the normal vector is. These are lots of symmetries there. Very convenient trick to write down the normal vector. And so, easy to write that down. And once you do, you notice that, well, this is a pretty easy dot product to compute. Right? I mean, there's all this garbage over here. All this stuff that factors out. This is scalar stuff that factors out. Really, we're doing a dot product of that, and it adds up to 0. And so we're done. Right? So, worked out really nicely. Here's another clue that this was going to work out well. The alternative is kind of unthinkable, right? I'm not going to give you all a question on an exam where it's just pages and pages and pages of tedious, brutal algebra, right? Y'all don't want that. I don't want that. I don't want to grade it. Y'all don't want to do it. Right? We're all on the same page here. Right? So if it's starting to look like, wow, that's going to be some nasty algebra. Okay, there's probably something. Something's going to happen. Something. Be on the lookout. Head on a swivel. Where's the trick? Where does it get easier? Where's the good fortune? Right. So anyway, that's what happens in this case. Okay. All right. So that does it for chapter 6. I'm going to go back now to chapter 4. So my substitute on Friday. Apologies that I couldn't make it on Friday, but he tells me that he talked through critical points in interiors. By the way, he didn't have a copy of this book, which is fine. He gave you, as he reported to me anyway, sort of a different but very reasonable perspective on how to do what I call unconstrained optimization, what you can think of as optimization in the interior of your domain. And so, roughly speaking, the point is, and let's look at this picture. If you want to eliminate this point here, by the way, notice I'm looking at a graph. Here's the point on the graph sitting above the point I'm looking at. If you want to eliminate that as a possible maximum, real easy to eliminate this as a possible maximum. There's the gradient. Gradients point uphill, right? We know that as you go in the direction of the gradient, the function is increasing. So go ahead. All right, you're in the interior. You can go any direction you want from that point. The gradient's non-zero. if you simply choose to say, look, whenever the gradient's non-zero, I'm just going to start moving in the direction of the gradient, and the function will be increasing. Now, if your goal is to find the maximum value of a function, a point that maximizes the value of the function, well, a point where the value of the function is still increasing couldn't possibly be the maximum you're looking for, right? If you're climbing a mountain and you're still going up, you're not at the top yet. I don't know. Does everybody relate to that? You know. So yeah, that's the argument. Now here's a different way to say it. Sort of the punchline then is if you find a point where the gradient is 0, your argument breaks down. Right? So how would I use the argument that I just made to eliminate this point A as a possible maximizer for my function? Well, go in the direction of the gradient. The gradient's 0. The gradient's not pointing in a direction. I don't have an argument. I cannot eliminate this as a possible maximum. As far as I know, it's the maximum I'm looking for. I can't eliminate it, right? So the reason that we do this, the reason that we take the gradient and set it equal to 0, it's not because this will give us maxima. It's because this represents points that I cannot eliminate as possible maxima. This equation represents points where my argument fails. This is not a successful argument. This is the losing argument of our process, right? So anyway, good news. There's only going to be typically a few such points in the interior, and those are candidates. Those are possible maxima. Now, I emphasize that there's also the question of, well, hey, what if the maximum you're looking for is achieved at a point on the boundary? That's a different thing, right? This argument about gradient only makes sense if you're in the interior, because only if you're in the interior could you eliminate a point by just going in whatever direction. If you were to take the gradient at that point, and it's like that, and say, I'm going to try to eliminate this as a possible maximum by arguing, well, hey, all I got to do is just go this way, and the function's increasing. Okay, well, yeah, but you can't go that way. You're not allowed to. There's no domain over there. We're looking to maximize this function whose graph we're looking at on this domain, and making reference to the fact that the function may or may not have a higher value outside of the domain. Irrelevant. Right? Okay. So, how to deal with boundary stuff, separate question. Bunch of details, discussion, but here's the conclusion. Oh, whoops. Here it is. If the gradient's 0, you got a critical point. By the way, if the function fails to be differentiable, then our argument actually, again, fails. Our argument was go in the direction of the gradient because the function will be increasing. It was a directional derivative argument that relies on the function being differentiable. So whenever the function fails to be differentiable, again, who knows? We can't conclude anything about what's going on there. So we have to call those critical points too. Excuse me. Okay, all right, so Professor Mella talked about all this stuff last time, went through some examples, talks about different types of critical points. Okay, here's what you're kind of expecting. Maxima, little mountaintops, right? Minima, little crater bottoms, I guess you'd say. But keep in mind there are other possibilities, right? There's saddle points, what I think should be called Pringle points. I feel like did I make that joke already in this semester? I feel like I did. I was trying to remember that. When did I say that? I don't remember what the context was. Maybe it was in the section on differentiability or something. Oh, yeah. Probably. Yeah. Okay. So anyway, that's one of the possibilities. It sounded familiar in my mind, but I just couldn't place it. What I like to call shoulder points. Right? This kind of looks like somebody's shoulder. Right? So it's kind of an inflection point in one direction, but it's a sort of a maximum in the other direction. That's a different thing, right? That doesn't look like this other one. That's not a Pringle. There are no analogs of these kinds of things in single variable calculus. The multivariable calculus is a little bit more sort of exotic in the sense that there's all sorts of weirdness that there's just no single variable version. Okay, so these are possibilities. And so I was arguing with myself before class started and trying to remember, and I couldn't. But did I show you all the monkey saddle? I didn't. Oh, okay. This is yet another kind of, this is a sort of a peculiarity of graphs of functions of two variables. The monkey saddle is what it's called. And here's a picture of it. Right, so you got a surface. Here's a better picture. Less funny, but more visible. So it's a surface where, yeah, it's up and it's down in different directions, but there's sort of 3 down slopes instead of just 2, because the monkey needs one for his tail. Right, so they call that a monkey saddle. People only need 2, people have 2 legs, so the saddle slopes down in only 2 directions. That's a regular saddle. This is a monkey saddle. And then there's I saw another one on the thing. Yeah, here, this is a alien saddle. And you can imagine, I mean, it's hard to, I don't have a physical image that I can show you, but it's sort of, as you sort of go around, it's like up, down, like this, but with 6 ups and downs. So I guess you could say that's an insect saddle, right? Because it has the 6 down slopes. Okay. All right. All sorts of weirdness that exists in 3 space. There's just no 2-dimensional versions of these things. Okay, somebody 3D printed one. That's pretty cool. All right. Okay. So Professor Mella talked about the second derivative test, and so I won't. Time being what it is, I'm not going to talk about that. But he's already spent some time on that. Okay, so I think he also kind of started the conversation with Lagrange multipliers. And let me just remind you what the argument is there. Let's suppose you're looking at there's a 2-dimensional version of this as well. I'm going to let y'all think that through. I want to do the 3-dimensional pictures because it's more challenging. Right? I'll do the hard part. Leave the easy part for y'all to work out. If you are confined to a surface, or said differently, let's suppose hypothetically you've already considered the interior, you found critical points in the interior, and you want to consider it now instead. Let's look at the boundary. How would I find critical points on the boundary? The argument goes like this. Suppose this is kind of zoomed in now on part of the surface. So here's my level set that I'm confined to, my surface that I'm confined to. Suppose at this point that the function you're trying to optimize has that vector as its gradient. And I argue, if this is the picture, then I can, just by geometric hand waving, I can persuade you there's no way this could possibly be the maximizer on this surface, on this green surface. There's no way that could possibly be the maximum. Just take off and start going. Now there's a temptation to say go that way, go in the direction of the gradient, but no, you can't, right? I can't leave the surface. I'm confined to the surface. It's total garbage to talk about, I just go in the direction of the gradient. But what you can do is go in the direction of the projection of the gradient. Right? Take the gradient, look at its shadow, if you will, straight perpendicular to the tangent plane. Look at that vector. Go in the direction of that purple vector. Well, as this is drawn, this gradient of f is kind of tilted. Right? When you look at the projection, that's a non-zero vector there. How fast is the function increasing as I go in that purple direction? What's the dot product of this non-zero vector with that non-zero vector with a not right angle in between them? function's increasing as you go in this direction. And as you go in that direction, you're staying on the curve, or at least, let me say that a little bit differently. You can stay on the curve say in a path like this, in such a way that at that point, that purple vector is your velocity vector. Right? So as you move along that green curve, the function is increasing. That couldn't possibly be a maximum. I therefore eliminate A as being a possible answer to my question. So this has got a lot in common with how we eliminated interior candidates, right? This being on the boundary instead. A lot in common. It's a little bit different in the sense that you have to look at a projection of the gradient, but it's not terribly different. And again, good news. This allows you to eliminate most of the points on the green surface. Most of the time, the blue vector will be, kind of tilted off at some angle, and they'll have a projection, and you can just go that way, and the function's increasing. You're not at the maximum yet. Okay. There's only a couple ways that this can fail. This argument works pretty darn reliably. A couple of little sticking points. The main one, at least geometrically, is this picture. Keep in mind this surface is a level set. This is where the constraint function g is equal to 0. That means that the gradient of g is always perpendicular to it. What if the gradient of f were also perpendicular to it? Right? My argument would fail here. If I say, go in the direction of the shadow of gradient f. Well, gradient f, the shadow is 0 vector. That does not tell me a direction. I don't have a direction in which I can argue the function's increasing. I got nothing. Right? I can't eliminate this as a possible maximum. So this is kind of the surface equivalent of saying the gradient equals 0. In the constrained situation where you're confined to the surface, you don't need for the gradient of f to be 0. You just need the gradient of f to be perpendicular to your surface. Or said differently, you need the gradient of f to also be perpendicular to the surface, also in addition to gradient g, which of course is always. Therefore, we need the gradient of f and the gradient of g to point in the same direction. And that's called the Lagrange condition of this Lagrange multiplier theorem. They call it. So I think Professor Mello talked about this at least a little bit. There are a couple other little sticky wickets. You got to worry about differentiability. Again, if the function fails to be differentiable, your ruling out argument is going to crash and burn because your ruling out argument uses directional derivatives and dot products, and that all requires differentiability. So you got to check for failures of differentiability. And there's another one. You need to worry about where the gradient of g is 0. It seems weird, but there's kind of two reasons why you need to worry about this. One is, if the gradient of g were 0, that would make the right side of this equation 0. But the only reason I wrote this equation down in the first place is all I really needed was for gradient of f to be perpendicular to the surface. If the gradient of g is the 0 vector, this could still be perpendicular to the surface, and the equation would fail simply because there's nothing you can multiply by 0 to get not 0. Right? So it's an algebraic, the statement, this is a multiple of that is not technically quite the same as these, vectors are pointing in certain directions. Right? So the geometric and the algebraic are not 100% equal. So anyway, you got to write down gradient of g equals 0 as a possibility as well. So any point satisfying this condition is what we call the degeneracy condition, for reasons that I don't have time to talk about, is also a critical point, called a degenerate critical point. And any point that satisfies this condition, the Lagrange condition, I like to call it Lagrange critical point. Okay. All right. So let's get an example done. Did Mela do an example, computational example of this stuff at the very end or something? Okay. I like this example pretty well. Let me go ahead and do this. We want to find critical points of this function defined on that domain. So we have a plane. This is a plane that does not go through the origin. And I'm looking at this function, x squared plus y squared plus z squared. This keeps getting bigger and bigger and bigger. Right? There's no maximum value of this function. But I could reasonably ask, what's the minimum value of this function? And it's not 0 because that would require it being the origin, which is not on our domain. So I want to know on this domain, where's the minimum value of this function? Okay, so differentiability is not going to be a problem. We're looking at a polynomial. The function never fails to be differentiable. So there's no differentiability critical points. Okay, all right. Well, we tried. What about degeneracy? Could this equal to 0? Could the gradient of g equal to 0? What values of x, y, and z would make this equal to 0? Well, that's crazy talk. I don't care what x is. 6 is never 0, right? There's no way that 6 or 3 or 2 will ever be 0. So this is not the 0 vector. So there's no degenerate critical points either. Lastly, here's our Lagrange condition. Now notice we have the gradient of f is posed to be some multiple of the gradient of g. All right. Notice that that vector equation is equivalent to this trio of scalar equations. And don't forget one other thing. I'm not just interested in any possible point anywhere that satisfies the Lagrange condition. The Lagrange condition is only of interest on our surface, right? So if there's some point out in the middle of space somewhere for which I can write this down, so what? It's got nothing to do with our question. Our question is on the surface that we were given, what's the minimizer, maximizer, what have you. So it's not just those three equations, it's those three equations and our original constraint together. Right, so I'm really looking for a point that satisfies these four equations. And notice you have four equations and four unknowns. And, algebraically, these can be hard. Lots of variables, right? It's a nasty problem in some situations. Now, there are techniques that work in different situations. I'm going to show you a technique that works here and that works often, but it does not work always. So this is kind of a sometimes kind of a deal. And here's the idea. The idea is solve for lambda in all three of the equations. Right? And then see what that tells you. So lambda, if you look at these three equations up here, on the one hand it's 2x over 6, it's 2y over 3, 2z over 2. Those three lambdas equal to all three of those things. Therefore, all three of those things have to equal to each other. And notice that I now have two new equations. Right? We had three equations. Three equations with four unknowns. Now I have two equations, three unknowns. This is called eliminating a variable. Solve for a variable in all of the equations, set all the results equal to each other, eliminates that variable. So we've made the problem a little bit easier of a problem. And of course that I can rewrite as these. If I can figure out what x is, then that'll tell me y, that'll tell me z. And okay, well, plugging in for what y is and what z is in the constraint equation does tell me x, and that tells me y and z. So there's your critical point. So the algebra is, it's a little, intense. And Lagrange problems, that just is kind of the nature of the beast. It's going to happen, right? So you got to be prepared for it. This is a good starter example. Eliminating lambda is a good trick. Like I say, it's not always what's going to work, but it's a good trick to work with. Here's one more example. Same function, f. And I want to find critical points on this ellipsoid. Okay, so different domain. Right, now, the degeneracy condition works out pretty nicely. Here's the gradient of g. Could this ever possibly equal to 0? And you can't laughably, you can't just kind of laugh off and say, oh, well, yeah, obviously 6 is never 0. No, algebraically, this really could be 0. Right? That first component could be 0. If x were 0, that first component is 0. That's real, right? So if x, y, and z were all 0, if I were looking at the origin, that would satisfy this equation. It's going to be tempting to call the origin a degenerate critical point. But it's not, because the origin is not on our ellipsoid. It doesn't satisfy the constraint equation. So who cares? Right? Who cares if we found a point we're thoroughly uninterested in that happens to satisfy one of the equations that we're looking at? It's got nothing to do with our question. Our question's on the ellipsoid. So not a degenerate critical point. It's inaccurate if you label this as a degenerate critical point, but it's really easy to lose track of what you're doing. So easy to you start writing down algebra and you just kind of get into algebra and moving symbols around and this kind of thing. And a lot of students will say degenerate critical point. That's wrong. Again, importantly wrong. Yeah. Okay, so heads up. Okay, what about the Lagrange condition? Well, here's the gradient of f, gradient of g. There's our Lagrange condition. Gradient of f is lambda times gradient of g. And write that down. It has these equations, and it's tempting then to say, well, there's no solutions. Because look, that first equation, doesn't that say lambda equals 1? And this second equation, doesn't that say lambda has to equal to a fourth? And that third equation, doesn't that say lambda is equal to a ninth? There's no possible way that a number could that lambda could be all three of these different things. Therefore, no solution. Very tempting line of reasoning. Again, don't make that mistake. It's alluring. It's especially alluring given the fact that, now I'm done. Right? There's no solutions. I don't have to do more painful algebra. So, this little siren song of convenience is super dangerous. Don't make that mistake. Here's why it's wrong. What this first equation actually tells me is either lambda equals 1 or x equals 0. Don't forget about the possibility. X could be 0. Right? I mean, if you rewrite this equation is lambda minus 1 times 2x is equal to 0. We have a product that's equal to 0. That means either this factor is 0 or the other factor is 0. It doesn't mean that this factor has to be 0. Okay. All right, so you got to consider cases one at a time. I mean, let's suppose that x is non-zero. If x is non-zero, now I can conclude that lambda is equal to 1. If lambda is equal to 1, I can plug that into there. Lambda is 1. That tells me that y is equal to 0 and z is equal to 0. Okay, so if x is not 0, then y and z are 0. And plugging that back into our constraint, y is 0 and z is 0, then x is plus or minus 6. Right, so you know, it's a little annoying and tedious, but you got to think it through. This is, by the way, this is case 1, right? If x is non-zero, then I get these 2 points. What if x is 0? Well, then there's a possibility instead that maybe y is the thing that's non-zero. Right? If y is non-zero, then that would mean that lambda is equal to a fourth. And if lambda is equal to a fourth, then these equations tell you that x and z are equal to 0, and that allows you to solve for y, and y ends up being plus or minus 3. And then again, there's the third case of z being the thing that's non-zero. So several cases to work out, lots of little details. Be real careful with this algebra. The main reason I like to show students this example is as a warning of don't be too sloppy and careless with the algebra and just kind of pretend that you can just cancel algebraically. Just, you know, you can cancel freely without concern, because sometimes bad things happen. So notice there are 6 critical points that we found, and if we were just a little bit careless with the algebra, we would have found none of those 6 critical points. Yeah. Okay. All right. So heads up. Okay. We are out of time, so I'm going to have to call it here. By the way, it is typical that we very often don't have time to get to the 2 constraint critical points stuff. It's not terribly different. The picture is harder to draw, but ultimately the theorem is very similar looking, and your Lagrange equation looks a lot like the original Lagrange equation, just with an extra term. Right? So if you ever find yourself with a 2 constraint optimization situation, it's not hard. Pick up the book and you can read this section at a time. Y'all are not going to be responsible for 2 constraint Lagrange problems for this course, so you can ignore all that stuff. Also, section 4.13. It is not rare that we don't have time to get to it, so y'all are not responsible for this either. It really, all it does is kind of bring together the ideas from sections 411 and 412. Again, if you find yourself interested at some point in the future, it's very readable. Okay. All right. We're out of time. See y'all later. See you at the final exam on, what's that, Wednesday morning. 9 a.m. Bright and early. Get your coffee.